Hi, today our topic is Biot-Savart law. Okay, let's consider that you want to find the magnetic flux density at a point near a current carrying conductor, or let's say a wire. So how can you calculate that? For that we have this Biot-Savart law. The law says the magnetic flux density at a point due to a current carrying infinitesimal of the conductor is. So here I consider infinitesimal length element. So I take the infinitesimal length element to be delta L. So here the word infinitesimal means infinitely small. In mathematical term, the length is approaching to 0. Okay, so here I consider infinitesimal length element to be delta L. And also I consider the magnetic flux density at this point to be delta B due to this length element. Then it says the delta B is proportional to I times delta L, where is the current and the length element delta L. And also it's proportional to sine value of the angle theta. Here theta is the angle between, I can show you if I draw a tangent here to this length element. Okay, and I can draw a line joining this length element and the point where you want to find the magnetic flux density. So angle between them is the theta. So here one thing you have to keep in mind, here current is moving in this direction, so I take the angle to be this one. If the current is moving in the direction, you have to take the angle theta to be this angle. Okay, so delta B is proportional to sine value of the angle between the tangent to the length element and the line joining length element and the point where you want to find the magnetic flux density. Also, the magnetic flux is proportional. So I can show you this is the between the length element and B. So I can write this length to be R. So the magnetic flux density is proportional to square of the distance between them. So here now I have three inequalities. I take this to be my equation 1, and this is equation 2, and this equation 3. Okay, now by taking my equation 1, 2 and 3 by 1 comma I can write delta B is proportional to I delta L sine theta over R squared. Now I can write this delta B is equal to mu over 4 5, where mu over 4 5 is the proportionality constant times I sine theta times delta L over R squared. So this is the equation that gives for us from Biot-Savart law. So this means the magnetic flux density at this point due to a infinitesimal length element. So here we have the magnetic flux density at this point only due to this element. So if you want to find the total magnetic flux density at this point, then you have to integrate this length element to the whole length. So in other words, if you want to know the magnetic flux density at this point due to this length, then you the flux density at this point due to the total length. So this is the equation we obtained from Biot-Savart law. So here we have introduced new term mu. The mu is called the permeability, and the value of mu in the free space, let's denote as nu naught, is equal to 4 5 times 10 to the power minus 7. Unit is this is Tesla over here, meter square, meter ampere per ampere, or Tesla meter per ampere, or Henry per meter. So this is the unit of mu naught. Okay, now let's do an example of Biot-Savart law. In other words, a practical application of Biot-Savart law. Before we moving into the application of Biot-Savart law, I forgot to mention one thing. We know this gives the magnitude of the magnetic flux density at this due to this delta L length element. As we know, the magnetic flux density is a vector quantity, so it has magnitude and the direction. So magnitude is given by the Biot-Savart law, and to find the direction we have to use right hand rule, right, or Maxwell's corkscrew moving direction. So if I use right hand rule here, the magnetic flux density is into the board. Okay. Here our first example is to find the magnetic flux density at the center of current carrying circular conducting loop. Okay, so let's consider the radius of this circular loop is R, and current in the loop is I. Now we want to find the magnetic flux density at the center here. So how can we find this? So to find this, now we are going to use Biot-Savart law. So first what we want to do is we want to consider a infinitesimal length element. So I am considering a length element from here vertically downwards. So this is my delta L. If you want, you can consider here, 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 wherever you want. So for my convenience, I consider it to be here. So we can write down the Biot-Savart law. Same place before, we can write the magnetic flux density at this center to be delta B due to this infinitesimal length element. So I can write that is equal as delta B is equal mu over 4 5 times I sin theta over distance from O to this length element is R. It's a circle, same. So that times delta L. Okay, here we have the magnetic flux density at this point due to this length element that is given by this equation. So what is the value of theta here? So to find the value of theta, we know we are going to draw tangent to this length element. So if I draw a tangent to this element, okay, and current is moving this direction, therefore I want to measure the theta angle is, we know whenever you draw a tangent to a circumference of the circle, always going to be 90 degrees. So this angle is 90, therefore sine theta is equal sine 90, and we value of 90 is equals to 1. So write the magnetic density at the point O due to that length element to be delta B is equal nu over 4 5 times I over R squared sin theta equals 1 times delta L. Okay, so now we get the magnetic flux density at this point due to this length element. Okay, and now I consider okay, so what is the circumference of a circle? We know if the radius is simple R, the circumference is given by 2 5 R, right? And now I consider there are capital N number of such length elements. That means you take this circumference and cut into capital N number of equal pieces. Each length is delta L. So I can write this 2 5 R is equal N times delta L, right? Okay, and now I am going to consider, so we know the magnetic flux density at this point due to this length element. So now I am going to consider the consecutive length element delta L. So here that I consider this length element. So due to this length element, the magnetic flux density at this point is the same value because the radius length is same and the angle is always going to be 90, so it also going to be the same value. Okay, and also to find the direction, both acting in the same direction, therefore the magnetic flux density due to these two both going to be delta B. So similarly, if I take the next consecutive, that is going to be another delta B. Like that I have to take capital N number of terms. So there is going to be delta B into N number of terms add up. So I can write the total magnetic flux density at this point B, that is going to be equal, we know delta B into N, right? So delta B into capital N. So now here I can write delta B in terms of this So B is equal mu over 4 5 times I over R square times delta L times N. Okay, so what is delta L times N? That is the total length of the circumference. That's the circumference of this circle. As we can see here, n times delta L is equal to 2πr. So I can substitute 2πr instead of this term. So B is equal mu over 4 5 r square times 2πr. If I simplify this term, I get B is equal mu I over 2r. So this is the flux density at the current carrying circular loop. Okay, now I am going to consider if there are simple n number of loops. If there are simple n number of loops, let's take in simple n to be the number of loops, then total magnetic flux density at the point O will be B is equal mu over mu I over 2r times. So if there are simple n number of loops, the total length will be 2πr into n, right? So here also it's going to be 2πr into n, then we have to multiply this by n. So I P is equal n I over 2r. This is the magnetic flux density at the center carrying conducting loop. Okay, and there are simple n number of loops. If the loop only one loop, the of n is 1, so you get this equation. Okay, here we have another two examples of Biot-Savart law, and here we are not going to discuss about the proof because it's not in the syllabus. So first thing is the magnetic flux density at a point distance r from a current carrying infinitely long straight conductor. So that is given by B is equal to I over 2πr. So to find the direction, you have to use right hand rules into the board. Similarly, if you want to consider another point somewhere here, so it's coming out of board. Okay, so this is the variation of magnetic flux density around the conductor with the distance. So when r comes to 0, it's like infinity, and when r goes to infinity, the value becomes 0. So this is the variation of magnetic flux density. And then we have the next one. It's a solenoid. So here we're going to consider the magnetic flux density variation along the axis of the solenoid. So it is in so to find the direction, so if you use here right hand rule around the this wire along the solenoid, it always shows into in this direction. So I can draw the magnetic flux density as like this. So this is how the magnetic field lines varies around this solenoid. So I can consider this is like N pole and S pole, and the magnetic flux density along the axis of this solenoid is given by B is equal mu capital Ni. So here I use capital N because this N is number of loops per unit length. If there are simple N number of loops and the total length of the solenoid is simple L, then I can write N is equal simple N over L. And the variation of the magnetic flux density, so along this axis it remains a constant value, and from here it's the drop downs. So when it goes to infinity, it becomes 0, and again the similar variation in the other side as well. Okay, so see you all in another video. Thank you.